Okay, so welcome. Good morning. So first I will start actually with some comments on the homework. So I now corrected the homework. It was very good, but at first sight, when I corrected the first copy of the person at random, I was a little bit worried, and then I realized what was going on. So I just want to clarify something, which I think you all know, but just in case you don't, let's just take 2 minutes to go over it together. So the comments on homework number 2. So the comment is on the first question. So what is the principal branch of the square root, and what does it mean to be a principal branch? So I realized actually, or it was underlined by the homework that it is ambiguous terminology. But you can mean several things by principal branch or a single valued, or do you demand that it's actually holomorphic or not? So, principal branch of the square root, okay? What is it? Okay? What is that? Is it the one defined by, so z is r e to the I theta? Is it defined by a? Is it, so square root of z is square root of absolute value of z, e to the I theta over 2. So far everybody agrees. But then, where do you put theta? Do you put theta in, so everybody agrees that you put theta in minus pi to pi, but then everybody does not agree on what you put here. So do you put this, or do you put this? Okay? So half the class did this and half the class did that, basically. And, so both of these are completely fine for this exercise, because now we're asking about the identity if square root of z times square root of w is equal to square root of z times w. So this does not really require any finer properties of this function. It does not have to be analytic everywhere it is defined. It does not even have to be continuous everywhere it is defined. But I still, I really want to say this just so that the people who wrote this don't put in some next exercise with the square root where it actually is important. They use this definition without, considering this further. Because here you have to understand that it is not analytic. Here it is not even continuous, okay? Not even continuous. Yeah, so when I first saw this, I started commenting, in red in the homework, like, okay, careful, about this thing here. Because to me, I always want to consider this automatically because I'm used to wanting to consider analytic functions, right? So I want to consider the analytic branch, where I actually remove the whole thing. So the point is, here it is single valued, but it is not even continuous. Here it is single valued, it is continuous, it's even analytic. So, most often to be safe, you will want to use this. The people who use this in the present exercise were not wrong. This is perfectly fine. I just want to say this so that this is clear. And usually when I say a principal branch, if I want to be precise, I can say a principal holomorphic or analytic branch, okay? And then it can only be this one, because this one is not analytic. So this is a way to make it clear. Yeah. So I think this is good for everyone, but I just wanted to make it clear, because otherwise this would be seen as if you need this to be holomorphic and you put this, then it is not a typo, it is a very big mistake, essentially, in complex math, because it means you have not understood the branch cut and what it does, why it removes the continuity. But in this exercise, you might have understood perfectly branch cuts and put this anyway, because you're right that it's single value.
But for practical purposes, what is the difference? If I add this point,
yeah,
and it will still be analytic with all the other domain.
Yeah,
we have a discontinuity on this branch, but the same on the other phase. It is also discontinuous on the branch.
Yes, but it's not defined on the branch, so the difference is that it's analytic everywhere where it is defined, simply.
Yes, but in practical purposes, we will not need that.
No, but all of this is, in that case, you might just say that for practical purposes, you don't need to put this at all, because you can just say it's multi-valued, and in practice, you restrict to some single-valued case. And this is what we're doing. So, I think,
probably one can choose the first one.
Yeah.
For when he's choosing just principal branch, and then he said that Z must be in C minus the negative. So he removed this line after.
Yeah. Some people said this. Yeah. No, so I mean, I'm saying for the homework it was absolutely fine, but I just think that, you know, a principal branch when you want to work with analytic stuff, it is this, the open one. Okay? So this was the first one. The second comment is not about the homework. It's about a proof I did last time. So I finished a proof, so comment on last time. Okay, so then I finished the proof. So I wanted to show the following theorem, that if f is analytic and the limit of z minus a f of z is 0 as z goes to a, then the integral of a rectangle over the boundary of a rectangle of f of z dz is 0. Okay, so integrated along the boundary of a rectangle, R. And I said that this integral was 0, and to do this I said that we subdivided this rectangle. So I had some point in the interior, and then I subdivided this into several parts. And I can do this so that this is a square, okay, and I call this R0, this smaller rectangle, but I can, without loss of generality, assume it's a square. And then I said, so we said, that, so we did some estimates, okay, and we showed that the absolute value of this integral, boundary of R, of f of z dz, is less than or equal to epsilon times the integral over boundary of R0 dz over z minus z0. You may remember this. And then I said, this is less than or equal to c epsilon, and then I said, oh, but c has to be uniform. Otherwise it doesn't work. And then I said, from memory, you can take C to be 8, but yesterday I didn't, you know, I had sort of not prepared this point. So I just had a look at it for 2 minutes, and it's very easy. So you assume this is a square. The side of the square is x, okay? So then when you are here, this distance is 1/2 x or more, right? So this means that the 1 over this absolute value, so this is greater than or equal to 1/2, so this is less than or equal to 2 over, well, 1/2 x, right? So this is less than or equal to 2x, okay? And then, of course, if you take the integral of dz times this over the boundary of R0, then this is less than or equal to 2 over x integral of dz boundary over R0, but this is just the length of the perimeter, which is 4x, okay? So this is 4x times 2 over x, which is 8. So I had seen this number somewhere, and now we know this is 8. So this is in fact less than or equal to 8 epsilon, which does not depend on epsilon, which is important. So we let epsilon tend to 0, and this integral has to be 0. Okay, so this was, yeah, now I fixed that. So now we didn't see any ambiguity in what was going on. Okay, so now we want to, so we talked about removable singularities at the end, yesterday. Okay, and then we will go on from there to talk about power series again, or power series expansions of holomorphic functions. Okay, so last time, so now we're going to talk about power series expansions. Okay, and so recall that, okay, we take f holomorphic function, holomorphic, and define now f1 of z to be the following function. So it is this difference quotient, f of z minus, this usual thing, when z is not a, and when z is equal to a, we say that it's equal to f prime of a, and this is, of course, defined in this u because we assume that u is holomorphic, so we can take the derivative. Okay? And then we remember, so recall, that if z minus a times your function, okay, so any function g, which is now f1, but if this goes to 0, as z goes to a, and g is continuous at a, then in fact g is holomorphic. Okay, in a neighborhood of a. So you recall this. Obviously, if I take this function and I multiply it, so obviously this tends to this because it's holomorphic, so it's continuous in a. When I multiply by z minus a, this is f of z minus f of a, the function is holomorphic, in particular continuous, so these values approach each other. So all of this is satisfied. So in particular, we note that f1 of z here is holomorphic or is analytic, and moreover, f1 of a is by definition, by construction, equal to f prime of a. Okay, so what I'm trying to explain now is where do these power series expansions come from. I'm trying to say that if you have a holomorphic function, then you can always expand it in a power series. But we have not shown this. Everybody sort of knows this as a fact, sure, because I've said it many times. But why should it be true? Where does it come from? So this is a little introduction on this. So when we consider this function, we used what we proved earlier about removable singularities to say that this is actually analytic, okay? And this was by construction. So then f1 of z, f of z is equal to, so now we just use this, so we say that f of z is equal to z minus a times f1 of z plus f of a, okay? So it's equal to f of a plus, right in the other order, f1 of z, where f1 of z is this, okay? And then I can continue this procedure. So let me take the second step. So by induction, well, then go on, so do the same thing. To f1 of z. So this gives you that f1 of z is equal to f1 of a plus z minus a f2 of z, where f2 is analytic, and so the same thing here. So if I take f2 of a, then it is equal to f1 prime of a. Okay, so I have this, and then of course we can replace in here f1 by all of this, and use the fact that f1 of a was equal to f prime of a. Okay, and then we get that this is equal to, so we get that f of z is equal to f of a plus z minus a f prime of a plus z minus a squared f2 of z. So you see we're starting to build by induction here our power series expansion. Okay, so by induction, what do we get? So f of z is f of a plus z minus a f prime of a plus z minus a squared And what is this, by the way? So the question will be, now what is, so this will be so this was f1 of A, so this is f2 of A, which is f1 prime of A. So what is that? Is that equal to f this of A, or is it something different? So we should check. So what should we put here? We want to put the derivative of f. So we have this. Okay. f2 of A is equal to, I mean, so of course we're gonna get here f2 of A and then plus something like that. Okay. Like we got here. But what is f2 of A? So to find this out, maybe we differentiate this line here. So f2 of A by width. Okay, so f2 of A is f1 prime of A. But what is f1 prime of A? So we can differentiate this. Okay, so differentiate star. Maybe you're already doing it in your head. Maybe you'll be faster while I erase. So differentiate star. So then we get that f prime of z is equal to, so f of A disappears, then it's equal to z minus A f1 of z plus f1 prime of z. Right? Sorry, no, what am I doing? You do something wrong? Yes, sorry. Yes. f1 prime of z plus I differentiate the other one plus f1 of z. Is this correct now? Okay. And then I want to put, I want to know what is, yeah, and I want, yeah, right, so I want to know what f bis is. This is what I want. Okay. So if I can't compute this one, then I get now f1 prime of z plus z minus A f1 this of z plus f1 prime of z, which is equal to 2 f1 prime of z. So this in particular means that f1 prime of A is equal to f this of A over 2, or actually over 2 factorial if you want to see. This is 2, but it is actually 2 factorial. So you will always get this kind of thing. So you see, so f2, and this was equal to f2 of A. So what we get here, now we can replace this by f this of A over 2 factorial. Okay, so I erase this and put it. Sorry, by f this of A over 2 factorial. Okay, and so on, plus fn of A over n factorial. Okay, plus fn plus 1, sorry, and then it ends at and then we have some last term here. Now it ended up having index n plus 1. But whatever. So we get such a thing, and then we start imagining that we should be able to make this rigorous, and we should be able to actually get the power series expansion up to infinity this way. Right? So, I mean, I like this explanation because it kind of shows a little bit how you can just understand by hand that there should exist one. Right? By just doing this argument. So I will now write down the formal statement of the theorem that we can sort of prove along this way, but we now understand that we should be able to prove, right? And then once I state it, I will give the formal proof. Okay, so we have now a theorem. Actually, there is this. Theorem So this theorem will now be a theorem that I have spoken about for 8 lectures, probably. So I had said already in the very beginning that not only are power series holomorphic, which we proved in maybe lecture 3 or something, but holomorphic functions have a power series expansion. So one way to say this is that, holomorphic and analytic are synonyms, as I have said many, many times. But holomorphic functions formally means you can differentiate the function in a complex sense. Analytic means you have a power series expansion. So holomorphic is the same as analytic. Okay, so this is now the theorem. This is the slogan of the theorem. So we already proved one direction, we will not prove the other. We will prove that if you are holomorphic, then you are analytic, so you have a power series expansion. So the statement is, so F holomorphic on some disk, okay, let's say centered 0, or some r greater than 0, then f of g is equal to sum of n, fn of 0 over n factorial times z to the n. Of course, if it's not centered in 0, you just translate it and you get the z minus a and the derivative in it. But I wanted to give a proof in 0 because that way I don't have to write 10,000 a everywhere. Okay, so now this was some kind of motivation. Now we give the formal proof of this, which is actually very nice, but it uses, of course, things we have done before, so it's not as basic principles as this one is. So now, the proof of this statement. So we have Cauchy's formula. Okay, and Cauchy's formula says that, so it's a representation formula, so we can write f of z as an integral. So the integral over c, which will be, I'll tell you in a minute what it is, of f of w over w minus z dw. Okay, so of course this is only true if, 1 over 2 pi I. So this is only true if the index or the winding number is 1. So clearly, I have not told you what this is, but I will have to tell you it's something with winding number 1, otherwise it is false. So what it is, C here is the circle of radius R0, where, so centered in 0, where R0 is smaller than this big R, so the function is holomorphic in some disk. Okay, and then we take, let's do it here.
Is it difficult to prove the last equality by recurrence? Or?
This one? No. Well, you mean that, you can prove this by induction.
It's not hard.
No, it's not hard.
So why we not prove only that this theory converges? It's sufficient, no?
Yeah, but essentially, if you look at what we will do, it's essentially what we will be doing. But this is somehow, it's going to be more streamlined. But you will see, essentially this is what we do. There is no magic. You have this thing and you have to show somehow it converges. So you will need some uniform convergence somewhere, and so you will use Weierstrass M test and so on and so on. If you still remember this useful piece of information from when we manipulated power series in the beginning. Okay, so let me draw the circles. So 0 is here. Okay, so this is R. Then you have some smaller circle here of radius R0. Okay, and then you pick some point in here. So this is R. So I haven't told you what R is. So R is the absolute value of Z. It's just my notation for that. Okay, so you have some circle, and we integrate along this. So this is the circle. The big circle is just the domain where you're holomorphic. So you integrate along this. This is C, and the winding number of C around 0 is 1. So the formula holds. Okay? Now, what do we do? Now we note, so this is the sort of nice trick that everything is based on. It's based on the following, that here in this integral, you have f of w times 1 over w minus z. And then you note that this 1 over w minus z, well, now we use these clever magic things that people do. What is this equal to? It's equal to 1 over w times 1 over 1 minus z over w. Okay? And this is equal to 1 over w times what?
The sum of
Yeah. So it's equal to this. And this is the big trick to get, because here you see a power series sort of start appearing. Okay? And the question we now have to ask ourselves is this convergent, first of all, because this is an infinite sum. Okay? So is this convergent? The answer is yes, this is convergent. And why?
Because w is in the circle.
Exactly. So convergent as this absolute value is less than 1. That's strictly so. Thank you. So it's strictly less than 1. So it's convergent. Okay? And even more, is this actually uniformly convergent? But, okay, I can tell you this now, but you don't really see maybe why we should need this. So let me just say why we should need this. So want to interchange now integral and sum. Okay? Because I said this was 1 over w minus z, so I want to integrate f of w times whatever that is. So to integrate an infinite sum, right? And then I will want to make the correct terms appear, I will want to interchange, I will say that the integral of the sum is the sum of the integral, even though the sum is infinite. And when do I have a right to do this? Of course you know that there has to be a condition. This is not always true, but if this is uniformly convergent, I can actually do this. So possible, since we have uniform convergence by this M test. For example, you can see this. Okay, this is a good moment to remember the M test. So you remember the M test was that you have the sum of some terms like this, f(n) of z, where n goes from 0 to infinity, and then you have that the absolute value of f(n) of z was less than or equal to n times an, where the sum of an converges. Okay? So in this case, we have the sum of z over w to the power n, where n goes from 0 to infinity, and the absolute value of this thing is less than 1. So this is less than or equal to r, where r is less than 1. This sum converges. We use the M test. It's uniformly convergent, so we can justify this step. Okay, and then what we get? So now we just interchange limit and sum. So f of z is the integral of this sum, so which is then equal to the sum of the integral of all these integrals. Okay, so it's equal to this of f of w to w, and then I have Zn. So of course I have Zn inside the integral, but the variable of integration is w. So Zn this is a constant. Okay, so I put it outside. Do you see? All I did was replace this by whatever I wrote there, 1 over w by this, and then I interchange the integral and the sum. I get this, and now what do we note? Well, what is this? Now we recognize this. Exactly. So by the Cauchy's integral, by the Cauchy formula, this is actually equal to the sum of the nth derivative in 0 over n factorial, okay, times z to the n. And now we are actually already done. So this is why I wanted to also show you this. This is very, very streamlined in my opinion. It's very nice. Okay? So we are done. And this is not a small theorem, right? So now we used Cauchy's integral formula, this representation formula, and the M test to show very quickly that actually holomorphic functions are analytic. And we already knew analytic functions are holomorphic. So now, for the first time, you actually have the right to use these as synonymous terms. Before I was just using them meaning the same thing, but now we actually know why. Okay, questions about that part? Otherwise, we will go into a whole new world.
You can use that in the homework?
What, the result or the... Yeah, I guess. Where do you want to use it?
To prove that something is a polynomial.
Oh, yeah, sure, yeah. Well, if you can use the Cauchy's formula, or if you can use the... that the holomorphic functions are analytic? Yeah, okay. You're allowed to use it. So, essentially, in all the exercises in complex analysis, once you know this, if you say, okay, a function is holomorphic, then you start by saying, if you're interested in some local property, usually the first step is writing down, so I have a power series expansion. And then you work with this.
I have a question. If
Yeah.
F z is entire function, then this power series is the base true for everything.
Yeah, exactly. So this is a good point. So you have this power series expansion, and it has a radius of convergence,
And
right?
the radius of convergence is infinite if f z is entire.
Yes. So for example, if f of z is the exponential or sinus or cosine, sine or cosine, then actually the radius of convergence here is infinite. So this is always true. So then you can write not only locally, but you can write that for every z. If you take the exponential, you have that for every z, e to the z is actually equal to, now this is how we defined it, right? But if we didn't define it this way, we could use the power series expansion to say that it's actually equal for everything. Radius of convergence is infinity.
And this means we can use the coefficients of this polar series, and we know the test, and then the square of 1 over n of this coefficient must be 0, yes?
The square of 1 over n times this coefficient?
Yes,
Must
the
be 0?
coefficient.
You mean because it converges, you want to deduce something about the coefficient?
Yes.
Is that what you mean? Yeah,
Because
sure, it's
if
possible.
inside the coefficients, we know the test, 1 over square of I by k must be...
Okay, so this is becoming a bit too detailed. I will continue the lecture, but we can take that after. But for sure, yeah, you can play around with this. You can say this converges. So, I mean, I tell you already now, if you have a question that says, suppose f is an entire function, and prove something, then always you say f entire, automatic first line is, okay, you write it as a power series with radius of convergence infinity, everywhere it is equal to its power series. So this is the first line. Even if it's just an abstract function, you write an abstract power series with coefficients an and z minus and z to the n. Okay, so you can use the power series expansion in 0 everywhere if it's an entire function. Okay, so that is how you usually start such exercises. Now, once we know this milestone, I will go on and discuss maybe my favorite topic in complex analysis, which I think is very nice. I will discuss zeros and singularities. So this is my favorite topic because I'm a complex geometer. So it approaches a little bit complex geometry, I would say, in its flavor, once you start studying these things. Okay, so can you give me an example of some analytic function and tell me what are the zeros of this analytic function?
What?
Give me some analytic function that has zeros and tell me what are the zeros of this analytic function.
The exponential.
Yeah. So the question is, can, for example, let me ask you this. So can a holomorphic function have infinitely many zeros?
Yes.
Yes?
The exponential minus 1.
Okay.
Sine,
Yeah, sine, cosine. So f of z is sine times. Maybe let me put a pi in there. That way, so has zeros in z, right? So in every integer point. For example, on the real line, I mean, so already it has infinitely many zeros. And then, of course, it has other. So, yeah, you can have infinitely many zeros. But there are nonetheless many restrictions on zeros of holomorphic functions. And one thing is that they have to be isolated. Okay? Yeah, so it means that if you have two different zeros, I mean, if you have a zero, you have to be able to find an open set around it which contains no other zeros. Okay, so that's what it means. So it has to be isolated zeros. Yeah, so we will study zeros and singularities because they are sort of dual to each other in some sense. So there are zeros, I mean there are many types of singularities, but zeros are dual to what's called poles. Okay, so we've already studied removable singularities. And essentially a pole of a function f is a zero of 1 over f. So, and 1 over f is also going to be holomorphic in an appropriate sense. So really zeros and poles are going to behave in the same way. So if you cannot have, I mean if your zeros have to be isolated, then also your poles will have to be isolated. And this duality is best viewed on the Riemann sphere. You remember? This extended complex plane, where infinity is just any point like any other point. I mean, there is nothing special about infinity from the point of view of Riemann sphere, which makes it extra beautiful. Okay, so we will get into this, but we will start nicely. So we will bring this point of view of a Riemann sphere in just a little while. So first, let me talk about zeros. And this theorem that we just talked about, that we actually have to be isolated. So we have the following. So f is some holomorphic function, or analytic, because now we proved it, okay, where U is some domain with some open connected set. Then we have, so do you know this abbreviation? If not, you should learn it. TFAE, very common in mathematics. Yes, the following are equivalent. Very common in mathematics because we have to give talks in 1 hour and we want to save time. So then the following are equivalent. So f is identically 0 on U. Okay, so that's obviously a very special function. So this is equivalent to the nth derivative being 0 for all n. And some a in U. Okay, and 3. So this is maybe the one that you think of most often. That f of zk, so is 0 for some sequence zk, okay, where zk is not equal to a. Okay, and for some, again for some A in U. Okay, this is not optimally phrased. What it means is that you cannot have an accumulation point. Okay, so if you have some holomorphic function, analytic function that is zero, okay, if it's zero on some open set, then already it is completely dead. It has to be the zero function. But we can say something even stronger. So we can say that if it's zero on some points that converge to some other point, okay, so this is zk, tends to A. So if it's zero on all of these points, then actually it has no choice but being the zero function again. So it means that this cannot happen if you are holomorphic. So for example, f of 1 over n equal to 0 for all n, like this, implies that f is identically 0 or that f is not holomorphic. Okay? So if it's holomorphic, then it has to be the zero function. Okay? Because this is an accumulation point, coming closer and closer to 0. So this is what this theorem says. So in particular, we have the following corollary, that zeros of f assumed holomorphic, okay, are isolated. Because precisely what I said, if it's not isolated, then by definition it has some accumulation point somewhere, and then it has to be the zero function. Okay. So of course, unless it is the zero function. So is this clear why we have this corollary? The zeros are isolated. Like in the example with sine, where you had infinitely many, but they were spaced out. They cannot be in a sequence that converge to somewhere. Okay, this has a name. Usually, this theorem is called the Identity Theorem. Do you recognize this name? Did you used to call it something else? Who recognizes this name? No one? Who has seen this theorem before? Okay, what did you call it?
In French,
Sorry?
Theorem des isolés.
Theorem des isolés. Okay. So, why do you think it might be called the identity theorem? So, identity means, identity can mean several things, but it can also mean that two things are identical. You know? So, there are several ways to, I guess, motivate this name. But so, this is one consequence. Another consequence is the following, that if, for example, f of zk is equal to g of zk on some sequence zk tends to a with some accumulation point, then they are actually equal. They are identical. Okay. So this is the most common way to show that two holomorphic functions are equal, by considering that the zeros are very different, and saying that if they have enough zeros in common, then they have to actually be equal everywhere.
So knowing the values of the function
Yes.
on set which is not discrete,
Mm-hmm.
give us all the functions. That's it, and converge.
Yeah, if by not discrete you mean something that has an accumulation point, which is, yeah. Exactly. So in particular, if you know which is amazing. If you have some holomorphic function on the entire complex plane, and you look at how it behaves in a tiny, tiny ball around some points.
Yeah.
So if you have, then there is only one holomorphic function that has this behavior in this tiny ball. If there is some other one with the same behavior, then they have to be the same. Which, however, is kind of expected because around this point you have a power series expansion. We know now, okay? And power series expansions are, they are defined in the function. So you could sort of guess this. But it's still a remarkable property. It's by far not true for any real differentiable function to make this standard comparison. This is as untrue as it can be in real analysis. But because all complex differentiable functions are analytic, this will turn out to be true. Okay, so the proof of this is actually very nice. So let's look at the proof. Proof. Okay, so the proof goes by proving the following. So we show that the third point implies the second point, which implies the first point, which implies the third point. So of course this is a very common technique. When you have many equivalent things, you go around in a circle, making a full loop. One of these statements are completely obvious, and it's one implies three. Okay. So this one is okay. So the first point is to show that 3 implies 2. So now let's do this. So by continuity, let's look at what we have to do. So we have to assume we have an accumulation point, and we want to show that all the partials have to vanish. Okay, all the higher derivatives then have to vanish. So by continuity of f, so this is the first thing that we note. So of course partials, what are they? They are constructed by this difference quotient as usual, f of z minus f of a divided by z minus a. So by continuity of f, not only does zk tend to a, but f of zk tends to f of a. Okay? Because we assume that zk goes to a. And f is holomorphic, so it's in particular continuous. Okay, so what does this mean? F of zk is equal to 0 everywhere, so f of a is equal to 0. So this is the first part. Okay, so now assume that this jth derivative in a is equal to 0 for all j up to a certain point. Let's see what we want to do here. Let's see, let me just read this. Okay, yeah, so we do a proof by induction. So essentially, we just assume that this is true for j from 0 up to n minus 1. Okay, so now we show that this was true for j equals 0 in particular. For the zeroth derivative is f of a, so this is 0. So now we assume this is true, and I have to erase this. So now we will show that it is true also for the nth derivative. Okay? So if it's true for the n minus 1 first, it should also be true for the nth. This is the nth. So by the power series expansion that we just showed, by power series expansion, we have f of z is equal to z minus a times n fn of z with fn analytic and fn of a is equal to nth derivative of a over n factorial. Summation. So, what am I saying? So this is a very common technique, right? So this is something that you will get used to writing. So immediately. So why is this true? So what I say is that f of z is equal to the sum of is equal to this around a. So now when I take z minus a times this, it's equal to this times z minus a times n. Okay, and then when I look at so what? No, sorry. I want to take out. Sorry, this is what I wanted. So this is equal to z minus a. This was. I did it the other way around. Sorry. So this is of course equal to z minus a times whatever you get in here. So yeah, all of them are 0. Exactly. So this is what. So this is equal to sum of n equal to. I shouldn't use n. I should use k. Sorry. So let's write it like this: k, 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 and it goes from k, not from 0, because the first n minus 1 were 0. So it goes from k equals n to infinity of this thing. So this is what it is. Okay. So I assume that all these were 0. This is k. This is k. This is k. Thank you. So I assume that this was 0. So this one starts at n. So I can divide out by this. So this is equal to times plus z minus a times a bunch of stuff. Okay? And so when I evaluate this in a, then all that's left is, so this becomes 0, or this vanishes, and it's equal to this. No? Clear? I mean, it's clear, it's true. No?
No, yes.
Yes? Yes, no? I write it again? No. Okay. So this is true. So this is, this is useful. So we have this. Okay? And now what do we do? It's not my...
Sorry, the last term is, why is it 0?
So this is equal to f of z. So this implies that f of a is equal to whatever I get in this when I replace z by a. Okay? Wait, sorry, what am I doing? I'm saying that fn of a, yeah, right. So this is fn, this is what I'm saying. This is fn of z. Okay?
Yes.
And then I take fn of a. Okay? Is clear? It's good. It's a constant plus z minus a times something plus z minus a squared times something. It's I evaluated it at a. So now where am I? So hence what do we get? So this is not the super beautiful part. The second part is the beautiful part of this proof. So 0 is f of zk, which is equal to f of zk was equal to this. So it's equal to zk minus a to the power n fn of zk. Okay. And zk, so okay, of course these k's are not the same, so don't be confused. And then if zk is not a, this implies that, so all of these things are 0, so fn of zk is 0, and this implies that fn of a has to be 0 by continuity. So fn of zk converges to fn of a, so by continuity. Okay, is this clear? So let's see. these f of zk's are 0? So, since zk is never equal to 0, this means that fn of zk is 0. It converges to fn of a by continuity. So, fn of a is 0, and fn of a was equal to this. Okay? So, so by induction, this concludes the proof. Of the pre-implies two part. Okay. Nothing really special happened. Now, however, let's consider the other part. Let's consider 2 implies 1. So let's first try to remember what was 2 and what was 1. So 2 was, we assume that all these partials, I'm sorry, not partials, these higher derivatives, again, these are 0 in A. And let's show that we actually, the function must be the 0 function. Okay? So now let's prove 2 implies A. And this is maybe my favorite method of proof. I'm sure you have seen it before, but it's always a pleasure. So consider the following set. Let's define a set A. So it consists of all the points in the domain of definition. This is where f is defined, okay, a function. So such that fn of z is 0 for all n greater than or equal to 0. Okay? So all points where these partials vanish. So this is the set of all points such that all the higher derivatives vanish. So again, I'm saying partials. So what do we want to do? We would like to show that this set is equal to U. We want this to hold in every point, right? Okay? So when you do this classical thing, how do you show that you define the set? How do you show that it's equal to U? Well, you probably know this trick. Somebody must know it.
We show that it is open, closed, and non-empty.
Exactly.
Is the region.
Exactly. So we show it's open and closed and non-empty. So by topology, you know that. So this, you might have noticed that I said that U had to be a domain. So it's open and connected. Okay. So it's a connected topological space, and the only connected topological spaces that are open and closed are the empty or the whole space itself. So therefore, we have to show that it's non-empty, open and closed in turn. So we just do one by one. So we start by showing that it's non-empty. Okay, non-empty, so this is okay because A is small a isn't big A. Okay, next one is to show that it is closed. Okay, so this is also not too hard. How do you show this?
Because the function n derivative is continuous and 0 is closed, is function, and the other thing is closed.
Exactly. So what you're saying is that, so if we write this down in what you said, in a beautiful one line, it means this. Oops. It's equal to this. And Fn are continuous. Okay? And then it's topology again. So this you know. Now, A is open. Okay? So, how do we show that A is open? So, follows by the power series expansion. Okay, but it has to be continuous. Okay, and so we have these three. We conclude that A must be equal to U. Now, warning, if U was not assumed to be connected, we could do the same thing, but then, so if you have a space with several connected components, and you know this kind of thing, somewhere in this space, then it means that it has to be identically zero on that connected component in which this happens. It doesn't have to be, everywhere. But you don't really normally consider polymorphic functions or complex analysis on a space with several connected components, because it is a local theory to be used for study of complex manifolds. So it doesn't really make too much sense to study disconnected space. But anyway, we have this, and then we have 1 implies 3 was obvious, so this finishes the entire proof. Okay, so this I think personally is very useful.
Why is open?
Yes?
Why is open?
Why is it open? Yes, I agree. This is the tricky part. So followed by power series expansion. So what does it mean? Let's write it down. Okay, so it means that f of z is locally, of course, equal to sum of fm of a over n factorial z minus a to n, which implies that fn of z is equal to fn of a plus n factorial over n plus 1 factorial, let's put it this way, times z minus a plus, okay, plus all these things, and these partials are all zero for logic. I don't know actually why I wrote this last part. Anyway, you have this power series expansion, and all these things were assumed 0, right? We're proving 2 implies 1. So all of these were assumed to be 0 for large enough n. So it means that, in fact, this function is sort of behaves as a polynomial in a small discrete discontinuous. By the way, this kind of method is used a lot in mathematics. So I know it's used a lot in your exercise sheets when you're a master's student and so on, but it really is used in research as well. So, in my area of research, in gallery geometry, there is something called continuity method to solve certain geometric partial differential equations. And there you define a suitable set that you want to simply show that it is non-empty, open and closed. And usually, so showing that it's non-empty is usually easy, okay, this is usually trivial. Then you have to show openness, and it's kind of hard, and then you have to show that it's closed, and this is super hard, essentially. So people write these extremely long papers with loads of tricks, loads of ideas, to try and show the last part that this set is actually closed, and then they prove some big theorem. And really, I mean, if you could perform, I mean, many extremely hard problems, like hardest problems in the world, can be formulated in this way. So you cannot just tell if it's going to be easy or hard. Like here in this case, it was easy, but you're not sure which one is going to be easier. But in some problems, it can really be Fields medal kind of level to be able to show just that it is open or just that it is closed. So it's this way. Yeah, I like this idea a lot. It's something worth remembering. Okay, so now we proved this theorem. talk about something, namely, I don't know what page I'm on, but I know I want to talk about zeros and poles. Let's see. Okay, so now let's talk about singular points. So now we showed this behavior that zeros are isolated. Now we have proven this. Now we want to talk about singularities. And we're always concerned with isolated singularities. So we look at the following definition. So an isolated singularity of a function f, like this, is a point. Let's call it, okay, I call it A, such that the restriction of f to u minus a, going from u minus a to c, is analytic, or is holomorphic. Okay? So, I mean, in our world we want to consider holomorphic functions, but we can also consider functions that are holomorphic outside a point, locally, right? So this is an isolated singularity. So, in some neighborhood of A, I should say, okay? So it can have multiple singularities, but if you look sufficiently close to each one of them, you get this kind of picture. Okay, so I should say, I should be more precise. So, f from u to c, so if such that there exists B, open neighborhood of A, such that when I restrict f to B minus A, so of course B is contained inside U, such that this function is analytic. Okay? So this is what I'm saying. So locally we have this picture that it's analytic everywhere except at this point. Okay, well, did I confuse you too much, or it was clear, it clarified what I meant? I hope I did. So, now, of course, examples of this. So examples are, for example, rational functions. Okay, so if, for example, f of z is like this, where p and q are polynomials, complex valued polynomials, with no common zeros. Okay, then f has isolated singularities at the zeros of Q. Okay, and it is clear that they are isolated. First of all, they are finitely many, and yes, this was now a polynomial. Yes?
The definition doesn't say that the isolated singularity is a singularity.
That very what? Sorry?
The definition doesn't say that the isolated singularity is a singularity.
Ah, yeah. No, but it's not. That's the thing.
What?
There is something called a removable singularity, which, for all intents and purposes, is not a singularity. So if I give you the function, f of z equals z, clearly it's an entire function. But I may pretend that 0 is a singularity because I don't understand what happens in 0. So I can say 0 is a singular point. But then you ask me, but what kind of singularity is it, really? And then I say, oh, it's actually a removable singularity. And being a removable singularity means it extends to a holomorphic function also over A, so it's holomorphic everywhere, so it wasn't a singularity. This is essentially what removable singularity means. It's a singularity that is not a singularity.
But in the world, singularity is a singularity.
Yes.
I mean, we have to change something in the function to remove the singularity. But
no, so it can be, so really, I mean, so a singularity can be simply somewhere where the function is not defined. So I mean, this is a very stupid example. But, yeah. So a singularity can be, for instance, a point where the function is, now I will use this word again, a priori, so at first glance, not defined. Okay. Where a function is not defined. So example, again this one, sin z over z. So then we look at this and we say, okay, outside of 0, this is an entire function, and this is an entire function. So outside of 0, this is holomorphic. But in 0, we have some worry, right? Because z becomes very small, so it might blow up.
yes.
In fact, it doesn't. So here, z equals 0 is a singularity. But it's a removable singularity.
Yes, that's what I'm saying. I'm saying here in the definition,
Yes.
we can set the previous example f of z equals z. It will satisfy the definition.
Yeah. Which is fine. I don't mind. I mean, it has no practical use to consider f of z equals z, and it would be very silly to think that you don't understand, that you suspect that it might have some singularities. So we understand this function, so we don't need to classify its singularities. But essentially any point of any function could be called a singularity, just that almost all of them are removable singularities. You see? This is philosophy. Okay? Yeah. So, this is a removable singularity. So removable singularities are points that aren't actual singularities. Because you can define this to be equal to 1 and 0. And then you see that it's actually an entire function. Okay? And it becomes entire. So it's a removable singularity. Now, so of course I can do the same thing, but I can do it with f and with g and h, where they are holomorphic functions. And then the singularities will be the zeros of h, the denominator. And the zeros of h are isolated. So you see also the singularities here will be isolated. So we prove recently that the zeros must be isolated. So we have the following overview. So you have 3 types of singularities. So the first one is this pathological kind. Okay? So it's a removable singularity. And this meant that this goes to 0 as it goes to A. This is what it means to be a removable singularity. Okay, or this is equivalent to that. So extends to holomorphic function on all of U, or all of B at least, and locally it extends to a holomorphic function. Let's put B. Okay? Because of course, maybe it's not on U because it might have several singularities and one might be an actual singularity. Okay? The second one is a pole. Okay, and I will tell you what that means. Essentially it will mean that f of z goes to infinity. Okay? But, so f of z goes to infinity, this tends to be interpreted as a very vague thing, but it's actually something very regular. Okay? So this means has a limit. And this is actually a very strong condition. Not all functions have a limit that is well defined when z tends to infinity, because now we are in a complex plane, right? So we can go to infinity in many ways. Okay? So going to this, it means that you can consider 1 over f has to have a limit that is well defined in 0. So 1 over f, so this means that 1 over f, so this is analytic outside, yeah. Okay, let me come to that next. So 1 over f. So in order to explain that well, I need to go into this Riemann sphere picture. So let me keep with that. And the third one is what is called an essential singularity. Okay, and essential singularities are basically all the remaining ones. So if you have a singularity, it can even be pathological, so it's actually a removable singularity, not singularity at all, or it's a pole, which is what we are mainly interested in, I would say. At least in my life, I think poles are the thing that we focus on the most. And then there are the rest ones, the terrible behavior. These are the truly bad guys. The ones that have essential singularities. So they have a singularity in the sense that they have no well-defined limit there. Some bad behavior. And this can be all sorts of things. For example, this discontinuity in a branch cut can be all sorts of stuff that go under this. And the definition of essential singularity is just an isolated singularity which is not removable or a pole. Okay, so we just bunch everything together that we don't like in the third category. This is what we do. Now, let's discuss poles.
Those types are types of isolated singularities, right?
Yes. That's isolated. Yeah, then you can have, as you grow up and do algebraic geometry, you might have all sorts of nasty singularities. You can write whole books of classification of singularities in algebraic geometry for sure. This is very useful. So now let's study this. Poles of order n. So you know that we can have an order of a 0. Do you know what it means to have an order of a 0? So for example, if I write down z to the power n, then the order of the 0, or maybe this, then it has a 0 and z equals a, but it comes with multiplicity n, so this is a 0 of order n of this function. Okay? So in the same way I can have a pole of order n, it would be something like 1 over this. This would give a pole of order n. So this is what it means. So, okay, if we have a pole of order n, so first of all it means that you have some holomorphic function. This one is holomorphic in some neighborhood of A. And f of z goes to infinity as z goes to A. So this is the definition of being a pole. So that means it's a 0 of 1 over f. So this is the definition. So definition, A is a pole of order n if and only if for f, if and only if A is a 0 of order n for 1 over f. Okay. Definition to keep in mind.
This is the definition right here.
This is definition. If you want.
Okay.
Yeah. It's a definition, or at most, to stretch, it's an explanation of a definition. Okay? It's not really up here. So you see clearly that you have this duality between between zeros and poles, right? Now let's see. So I have like maybe 8 more minutes. So let me just see what I want to try and do.
Well, the order of the zero is just defined for polynomials. So, what is the order of the zero? More general function.
So if you have this f of z is equal to, so in general it is equal to this. So let me just write it with a, even though we know what these coefficients are. Okay? And then there exists smallest, well, then this am, so let's say that am is non-zero, okay, but aj is 0 for j less than n. Then n is the order of the zero of this function. Okay.
And in our case, f is analytic at 0.
Analytic at 0, so I'm talking in the neighborhood of A, or what? So I'm looking at, I picked some point A in the complex plane, and I look in the neighborhood of this point.
1 over z, 1 over f is analytic.
Yes, exactly. Yeah, so that is a good point. So you see, so f is defined outside of this point A, okay? So it's analytic outside. F is analytic outside, and here we have some singularity. We have a pole. So 1 over f is also analytic outside, okay? Because here everything was fine. And it's another. So 1 over f is analytic in a neighborhood. And this is actually a removable singularity for 1 over f. As you said.
You are saying that f has no zeros in its domain, right? We are supposing.
Yeah. Which we always can. Because so all of this builds on taking a local picture. So whenever I draw something like this, means that globally there are zeros and there are poles and there are all these things around, but they're isolated. So I can always take a small enough domain so I can forget about all the rest. And I study it in the neighborhood of one of these zeros or poles. So I can assume that in this neighborhood both 1 over f and f are holomorphic away from A. Okay?
But the isolation is about singularities, not about zeros. So it
So
might be.
It's about zeros, not singularities. So we showed that zeros of holomorphic functions are isolated.
Yes.
Yeah, this is the theorem. So remark about this. So the remark is that so if A is a pole of F, then so in particular this holds true. So 1 over f of z, so this is a 0 of, so already this has a 0 in A. So in particular this is this is kind of stupid, but in particular this holds. So A is a removable singularity, is what I'm trying to say, for 1 over f. So you see, it's quite nice. So it means that if you have a pole somewhere, then locally 1 over this function is actually behaving nicely. It's an analytic function there. Simplest possible example, 1 over z has a pole in z equals 0. And 1 over z, which is z, is analytic in a neighborhood of 0 Of course, it's entire, but this is what I can say in general. So this behaves nicely. So this was kind of your remark, right? That 1 over f actually has a removable singularity if f has a pole at this point. Okay? So, who has heard about Laurent series expansions? I guess everyone. So, you remember what the Laurent series is? Maybe you didn't hear the name. Maybe. Let's say it's a power series expansion with negative coefficients. Okay. Actually, I'm going a little bit fast. I forgot one definition. So the basic object of study here is Meromorphic function. I'm not sure everybody heard this name. Did everybody hear this? Who heard Meromorphic? Good. So, a function f is meromorphic if it means to be meromorphic means that you're analytic outside of an isolated set of poles, right? Poles or removable singularities. So this is what it means. So a function f is said to be meromorphic. Okay, so we had holomorphic functions before, now we have meromorphic functions. If and only if it is analytic or it is holomorphic outside an isolated set of points, set of poles, in fact. Okay, so an isolated set of poles. Well, a set of isolated poles. Set of isolated poles. Poles are always isolated. Whatever. You know what I mean. Okay. This is the difference. Set of isolated singularities that have to be poles. So a meromorphic function cannot have essential singularities. Okay? So typical example again is the rational function. Okay? Typical example is f over g, where f and g are holomorphic.
And 1 over sinus is
1 over sin z?
have infinite isolated poles.
Yeah, so I'm saying isolated, but not necessarily a finite number. Right? So, there is a very natural point of view of it. So what I will show, so time is almost up, but let me just tell you what I will do with this. So first of all, meromorphic functions, very, very nice object, very natural object of study. So instead of just studying holomorphic functions, we allow some nice singularities, which are the poles. And then, so if you think of a rational function, so in the singularities, they are still behaving nicely, it's just that they have a well-defined limit that happens to tend to infinity. So g over f behaves nicely around that point. So if you look at these functions very naturally on this Riemann sphere, on C hat, so you can do it. Okay, and then you have the point north pole here, which is infinity, and then you have the 0 here, but you see that they are really the same. There is no difference between 0, infinity, any other point on this sphere. And you map this one to this one with a Möbius transformation, z goes to 1 over z. Okay? And with this Möbius transformation, you map the entire lower half sphere, you map it to the upper, the lower hemisphere to the upper hemisphere. So, this goes into the theory of Riemann surfaces and complex manifolds. But really, it is very natural to do this. And then you can even talk about zeros and poles at infinity. Okay? So you can say even such a thing as definition. So f has a pole at infinity if and only if. So what should we call a pole at infinity? Well, infinity is 0 viewed under this map. So if and only if f of 1 over z,
The limit of this
has a pole in 0. So this is the viewpoint. Because really, I mean, if you take away one point, with stereographic projection, you have a complex plane. But if I take away another point, I also have a complex plane. Okay? And this is when u 0 in my new complex plane. And I map one to the other via this z goes to 1 over z. So infinity is a point like any other, and you can talk about singularity zeros at infinity by considering f of 1 over z in 0. So this is what you do. So, yeah. I will leave you with this. Next time I will tell you, I will show you how to find Laurent expansions, and then go from there. You have all sorts of nice things, including a very, very quick proof of the residue theorem, actually, which is very nice, that you will get from this. So, okay. If you have any questions?